Okay, it should be recording. So hello everyone. I'm going to present a paper about snapshot ensembles, which pretty much tries to get the benefits of training ensembles and using ensembles without the drawbacks of training them. So going back to the basics, when they mention ensembles, they are talking about bagging, which is probably the simplest case of ensembling, where they train several models with the same hyperparameters. And because they are initialized in different places of the loss landscape, and because they have the training data should be shuffled, these two sources of randomness will result in very different models, which, although all of them should have similar metrics, similar performance, the examples that they classify incorrectly should be different. And therefore, if you combine the information from all models, you can obtain things like, is my ensemble certain or uncertain? Or can it improve the global accuracy if I average the predictions? And usually the answer to these questions is yes, you can improve a lot the performance of your final model if you get to do the ensembles. The problem is you have to train the same model multiple times. So once for every member of the ensemble. So if you want to have an ensemble of 10 models, you have to spend 10 times the computing resources, which is very inconvenient. Also, at test time, you need to evaluate each member of the ensemble. So you get also, again, 10 times the cost, which is super, super painful for some cases. If you have things like real-time latency, etc., it's very bad. So this paper tries to minimize the cost of training those ensembles. The test part remains the same. They just want to simplify in terms of resources, the training part. And that's why they say train one, get M for free. So they claim that they can obtain an ensemble of multiple neural networks at no additional cost. I'll go through the paper, and by the end, I'll give a bit of my opinion as a devil's advocate about the paper. They assess the paper mostly on image-based networks, but that should be no problem. The key idea is actually very simple, and it's depicted on this image. When you train a single model, you are on the regime on the left. You start from a random point, and you gradually go towards a place in the loss landscape that has a low loss value, which should correlate with a high accuracy. In this case, they are concerned about accuracy. And their idea is to control the learning rate so as to go through multiple local minimum, and at each local minimum, they take a snapshot of the network, and they use those snapshots as members of the ensemble. And by averaging or by doing a majority voting of these multiple snapshots, they claim to have superior performance with no additional training cost. So the hardest part about this paper, which is very simple, is how to control the learning rates, and why controlling the learning rates allow us to obtain multiple snapshots of the local minimum. So the key argument that they claim is that the stochastic gradient descent tends to avoid sharper local minima. What they mean by this is that if you have a very deep peak with a very high gradients, there is a significant chance that your model, while it's training, just skips over it because of the multiple gradient updates from the mini batches. If it was using all data at the same time, it probably would go towards that spiky valley, but that's a negative aspect of doing the gradient descent, the non-stochastic version of the gradient descent, because it tends to get stuck in local minima. However, if you are close to one of those places with sharp local minima and you decrease the learning rate, so you make the steps smaller, it is likely that your model go to those valleys. So what they mean by this is that if you have a high learning rate, you just skip those points. If you have a lower learning rate, you go to the closest local minimums. So if you control your learning rate, you can select between exploring the space and exploiting the local minima. So it's again the exploration exploitation trade-off. They do it in a way that they call it annealing, which is a common technique in multiple metaheuristic algorithms. And it comes from controlling metal, but that's besides the point of this presentation. The idea is that if you want to heat up, if you heat up your system, if you add entropy, you can move around freely. If you cool down your system, you decrease the entropy, which in this case corresponds to decreasing the learning rate. You can exploit the local benefits. So they pretty much, let me move to another picture. They control the learning rate of the paper so as to obtain a loss with this shape. So if you follow the line in blue, it's the standard learning rate scheduling, where you have a certain learning rate for 50% of the time your model is training. Then you decrease the learning rate by a factor usually of 10 for a 75%, from 50 to 75% of the training. And then again, you decrease the learning rate by the same factor, usually 10, and you converge to a good solution. So this is an annealing process, but with very aggressive steps. So constant learning rate, big step, constant learning rate, another big step, and you converge to a good solution. And what they claim to do is if you gradually change the learning rate, but very fast, you can converge to a good solution. But if you happen to increase the learning rate to its original state, again, your model will get out of the local minima is stuck on. It will increase the loss significantly, but is free to explore new regions. So they use a thing they call cyclic cosine annealing, where they control the learning rate by a cosine function. But it's not a proper cosine function where you start from 1 and you gradually go down to -1 and then gradually go up to 1. They do a modified version of that. So they start on 1, they gradually go down to -1, so the first half of the cosine function. And then instead of going gradually back up to +1, so the other half of the cosine function, they just reset the function. They go back to stage 0. So by doing that, they can create these training loss shapes. So the idea is they start with a very high loss. They gradually decrease it to a very low value. And please take into account that the last member of the last iteration of this function will have a learning rate of 0. Therefore, well, that the last, they skip the last iteration, but they get very close to 0. That's the point that we need to take from here. And when they are at that stage, the model should have a low validation loss and therefore high validation performance, whatever metric you are selecting. And that at the next stage, because of this function, they reset the learning rate, and then they go up to having a high training loss because they are again exploring the loss landscape. So you might wonder now, what is the difference between doing this, so gradually shifting the learning rates and obtaining the snapshot ensembles, and doing the normal ensembles? Because the normal ensembles can also have that, you can also do that learning rate pattern. There's nothing to prevent you from doing that. The difference is when they restart, when they increase the learning rate, they start from the low loss point that the previous snapshot had. So it is a model that is continuously training in opposition to the ensembles where you reset the all parameters for each ensemble member. So in the snapshot ensemble, you are following a trajectory that changes between exploration and exploitation. And with the normal ensembles, you are just doing the single model case, but multiple times, and you gather that up. So as you can see, the They have 4 pages to explain this, which is a concept that is actually very simple. Another important detail is that they say that at test time, they don't use all snapshots, because the first snapshots are more concerned with getting into the point of the loss landscape where they can have decent performance. And the last snapshots usually have a much higher test performance. So they say that they discard the first members, and they will go a little bit more into detail in the results. So half of the paper is actually concerned to results, because they want to make sure that everyone agrees with their main claim, which is we can get better performance without any extra training cost. To do so, they use standard ML architecture, so they don't try to reinvent the wheel here, and they use the standard dataset, so CIFAR10, CIFAR100, the Google dataset where they have the doors at the numbers at the doors, and tiny ImageNet. They also use ImageNet on other benchmarks. And for each case, they consider multiple examples. So for single model, it's the standard ML model that we are used to, but with dropout equals to 0. Then they consider dropout of 0.2, because they explain that dropouts can be considered as some sort of intrinsic ensembling, because you are training multiple models at the same time that share a lot of weights. They also consider a no-cycle snapshot ensemble, and by no-cycle snapshot ensemble, they mean instead of doing the cosine scheduling of the learning rate, they do the standard scheduling of the learning rate, where they train 50% with a certain learning rate, then they divide the learning rate by 10, run it for 25% of the train budget, decrease the learning rate by a factor of 10 again, and train for the remaining of the training cycle. By single cycle ensembles, they mean the standard ensembles. So you train a model for, imagine that we are doing a snapshot ensembles with 6 members. When they say they are comparing against the single cycle ensembles, they are also using the same training budget, but with that training budget, they will create again 6 ensembles. So they want to do an apples for apples comparison. So comparing the same number of ensembles of the snapshot ensemble versus the standard ensemble. I think single cycle is a bit misleading. They should just call it ensemble here, but I digress. By snapshot ensembles, they consider 2 different learning rates. So the 0.1 is the learning rate that is used for the other cases, and 0.2 is a modification that they experimented with and got better results. From this table, a quick overview is that from the test, they have realized the snapshot ensemble beats all the cases. So it's amazing, but is it? Let's see. So important things to take into consideration. So somewhere around here, I think it's further below, perhaps. Yes. They say that if we look, sorry, let me try to find the correct image. They have a perfect image for that. I think this one is the best one. So on this image, for instance, so the third image counting from the left, they are doing the DenseNet 100 for the CIFAR10 with the learning rate of 0.2, so the learning rate bigger than the other cases. And on the y-axis, you have the test error. On the x-axis, you have the index of the snapshot. So from left to right, you have time, pretty much. So on the first snapshot, you have a training error that is bigger than the baseline. So by the baseline, they mean a single model. On the second snapshot, it's close to the baseline, and from the third snapshot onwards, the test error is lower. So if you look at this and if you read their description, you'll conclude that the first snapshots are gradually going towards better places in the loss landscape, and the last snapshots get the benefit of that because they start in a good position. But that has a drawback that is completely missed in this paper, which is related to the previous presentation that Carlos did last week, which was concerned about measuring uncertainty on ensemble-like techniques. And this paper actually was the closest we can get to proper ensembles according to their metrics. But an important detail to take into consideration is that you start where the previous model finished. So you don't get to fully explore the loss landscape. You don't start from a random position. You start from some place that was given by the previous ensemble. So you don't get the information diversity that is very, very useful to estimate uncertainty. So although their technique can be used to get higher accuracy compared to the baseline with the same training budget, you don't get the same benefits in terms of trying to estimate uncertainty and some other benefits of ensemble. So you don't get the diversity benefits of ensemble. Although they mention that their method is a good trade-off between accuracy and diversity, probably not using the correct terms, but they mention diversity. They don't actually measure the benefits of diversity, which for me is a very big, important part about ensembles.
Can I add something there? Because,
yes.
So related to that, because they make a claim very early in the paper, which they never actually tested, but would have been interesting to test, which is that if you take that case where you actually want the diversity of the loss landscape, so a bagging ensemble method would require you to do 300 epochs with six different models. So you get 1,800 epochs of budget, so to speak. So they say that you can get that. So if you have the budget to do 1,800 epochs, you can do 6 snapshot ensembles and ensemble that. And then that gives you that sort of benefit of having having started from several different places of the loss landscape, and also the benefit of exploring different local minima. But they never verified it, which I think would have been an interesting experiment for this paper.
I'll go to that point later on the quality of their claims and the quality of the things they assess. Meanwhile, we have a question in Q&A. Does the final non-ensemble model, the last model trained, end up at a much worse minimum because of the annealing process? Does this add upper bound to performance? I ask because I don't usually train with annealing. So I think they mentioned that somewhere in the paper, not sure, but at least in figure 2, you can see that the final loss, the loss of the last model with the annealing, is very close to the loss of the normally trained model. But they never trained a full thing with annealing, so I don't know if this answers your question. They claim that doing snapshot with annealing the last model of snapshot with annealing should have roughly similar results compared to the standard training procedure.
Yeah, it's also annealing. Annealing is just a fancy word for saying that you're going to put the learning rate on a regime. So the standard learning rates scheduling, it's also an annealing technique. They pick this particular annealing because they want the loss to converge somewhere very quickly, to converge to a local minimum very quickly, and then hop out of that minimum to go to the next local minimum. So I don't think it puts an upper bound on performance. I think this particular annealing method is very bad if you want to do sort of a regular training schedule, because you'll converge very quickly to a local minimum, and then you lose the benefit of stochastic gradient descent, which is, well, you can actually skip over small minima and just go to places where there is very big gradient, where the minimum is better behaved, meaning that there is a smoother landscape around it.
Mm-hmm. And if you read the details on page 4, they say that they do this annealing at a step basis and not per epoch. So it's very fine, a fine grade annealing, which means that given the cosine function, it will get away from the maximum learning rate very, very quickly. We also have another question, which is ensemble errors are not calibrated probabilities, even if independently started. Would the different minima be independent? Good question. I'm not sure if the ensemble errors are more or less calibrated than the normal models. Do you have an idea about that, Carlos?
So I think what we saw in the last paper is that ensembles tend to be better calibrated than just a single deep model, which is why they are sometimes more interesting to make forecasts. It's not guaranteed that they will not be overconfident, but they tend to be less overconfident than just using a single model.
Mm-hmm.
And with the different,
yep. Yeah, that second part of the question is they are not entirely independent. So on the paper that Carlos presented last week, we could see that the diversity for the snapshot ensembles grow in like a logarithmic like curve compared to the traditional ensembles. So if you are comparing a snapshot of 5 versus a normal ensemble of 5, probably there's not a big difference. But if you compare a snapshot of 100 members versus a normal ensemble of 100 members, you'll notice a big difference according to the paper presented last week.
Yeah, I think that in that scenario, if you have a budget to train 100 models, it's better to do several different snapshots instead of just a single one.
Yeah. So moving on with the results. So we can clearly see from this table that doing snapshot ensemble is better than not doing any ensemble at all. But if you compare with the single cycle ensembles, which are the standard ensembles, so they divide the budget in the same way as the snapshot ensembles, the difference, and they use the same learning rate regime. The difference is every time they create a new member, they reinitialize the weights randomly. And if you look at the difficult data sets, such as CFAR 100 and ImageNet, you see that for some networks, the performance of the normal ensembles is pretty close to the best performance that the snapshot ensembles gave. And this is the main source of, for me, the main source of criticism to this paper, because for the snapshot ensembles, they tried a large array of parameters and they publish here the best case. And for the single ensembles, they just copied a set of parameters and they compared it. So they have a much higher degree of, they have many more degrees of freedom for the snapshot ensembles compared to the single ensembles. Moreover, there is a cool set of results that they show on figure 4, which is, let's try to compare the snapshot ensembles versus the single ensembles as we change the training budget on these two images on the left, and on the right as the number of models increase. So let's go first to the image on the left. On the image on the left, we see that if we have a certain training budget and you divide the training budget in the same manner for the snapshot ensemble and for the standard ensembles, you see that for an easy data set, such as CFAR 10, the snapshot seems to be better for the values they publish. We don't know what happens if they kept moving the budget to the right. However, for CFAR 100, a complex data set, we start to see that for a large number of epochs, the standard ensembles are better. And on the image on the right, for me, this is the biggest flaw of this paper. They try to compare what happens if they keep adding models to those two strategies. So if you keep adding models to the snapshot ensembles, considering 50 epochs per model, and if you keep keep adding models to the ensemble for the standard ensembles using 300 epochs per model. And of course, the standard ensembles will beat the snapshot ensembles because it has more epochs per model that is expected. But the real question is, what happens if they keep adding models with the same 50 epochs per model cost? Or the other way around, if they keep adding, if they compare snapshots with 300 epochs per model versus true ensembles with 300 epochs per model. Why am I going so hard about this? Because if you read the page before, actually the image number 3, as we discussed before, we know that the first members of the snapshot are concerned into getting into the correct area of the loss landscape. And they always compare snapshot ensembles and the normal ensembles, giving the same separation of training budget. So if we have 300 epochs, we divide both cases by 6. However, they never compared the case where they have the same number of epochs for both cases, but they do an asymmetric, not asymmetric, a different number of models. For instance, 300 epochs with 6 models of snapshot ensembles versus 300 epochs with 3 models from the normal ensembles. And my suspicion is that if you are flexible about this parameter and you try to compare these two cases, I would put my hands on fire that the normal ensembles would be better, but I'm speculating here.
So I think that they do show that so in that figure, in figure 4, they do show that the true ensembles are better, but they're making a comparison in the budget. So if you see when you say, well, let's say that so the total budget is 300 epochs, and then they say so the total budget is 300 epochs, so you can divide your snapshot into 6 ensembles and do 50 epochs for each member, right? So that's the red line. So what happens when at the end you use 1, 2, 3, 4, 5, or 6, and that's how the test error goes down. And then they say, well, let's say you wanted to train 2 models, but using true ensembles, you would have to do 300 epochs on each of the models. So that 2 there is actually a 600 epoch budget.
Yeah, of course, but that's not an apples to apples comparison. Ideally they should keep the training budget constant and try running the normal ensembles with not necessarily, so you keep the sum of epochs constant, but you change the number of ensembles. So in how many slices you divide that, and they never made that comparison. Because
they did that before, no? They did that up there. They showed if you have a constant budget, so if you go up this one, so yeah, you have the single cycle ensembles.
Mm-hmm. But they divide the single cycle ensembles with the same number of divisions as the snapshot ensembles.
Yeah, so that's what you were saying. You have the same budget, so you have 300 epochs to train your ensembles, and you train 6 ensembles starting at different points, 50 epochs each.
Yeah, but probably the ensembles would be better if you had 4 ensembles with 75 epochs each, because they have shown that the first rounds of training are concerned into moving into good positions of the loss landscape. So they never allow the full ensemble models to get into good positions. So by keeping that parameter fixed, they are not able to see the best side of the ensembles. They are making comparison with a suboptimal case.
Yeah, well, then you have to increase the budget. So that's the first figure. So the figure that shows both training regimes, that one down.
This one? Yeah.
Down. The second one.
Second one? Yes.
Yeah. I think this one shows that to get to the good place, you need 300 epochs, right?
Yeah.
So.
But they can use the cosine annealing for the ensembles, but instead of doing 6 divisions of 50 each, they could do 4 divisions of 75 each, for instance. They never made that comparison. And I'm arguing so much about this because they also say that these first epochs are concerned into getting into a decent position. So if you keep doing a short training cycle for the ensembles, you'll never allow each member to get into a good position. Therefore, you'll have worse performance. But again, that's a hunch. Like, I'm arguing that this paper should have done a proper comparison with this. It is.
I mean, that would have been an interesting comparison, but it would increase the size of your experiment exponentially, right? Because you have to do every combination of, like, how many divisions do you want to do?
Of course.
I mean, it's really tricky, right? Does anyone else have an opinion on this matter that would like to express it? Just raise your hand, and we'll happily give you. Looking at figure 5.
5. This 5, yes. Looks like the. I don't think they ever. So the question is, if you look at, I don't know if the other attendees can read the questions or not. Can you please raise the hand if you are able to see the questions in Q&A?
Okay.
I see one hand.
Yes. Okay,
2 hands. Cool. Okay, they can see. Okay, good. So I don't think they ever assessed just the. Oh, they can only see the questions when you have answered them. Okay. So the question is whether they have assessed just the final snapshot compared to the other things. And I don't think they ever assessed the last snapshot alone. And the motivation behind this question is the figure number 5, which I didn't talk about, where they compare the test loss. If you do an averaging of the last snapshot with the other snapshots. So just an averaging of 2 snapshots with an averaging weight of lambda, where 0 is just the first, second, third, fourth, or 5 snapshot, and 1 is just the 6th snapshot, and this is what happens in between. And we can see that the 3rd, 4th, and 5th snapshots are when averaged to the last snapshot, they don't change the result that much, which probably indicates that they are very close in the parameter space, because we know that the training starts from the same position, therefore it can't have gone very far. So they don't assess just the last model to compare the last model versus the full thing. And the other question, could they have gone lucky and with only one initialization location find a reasonable solution for the test data? Repeating these multiple times with different initialization may also be interesting. Definitely, I agree. I mean, nowadays a good deep learning paper should like do multiple instances of what they are proposing and show the median or at least the average of the results, because yes, you can get lucky. I mean, there are many people that say that the random seed is a hyperparameter. So yes, they could have gone lucky, assuming that they have enough resources. So yeah, the last part of the paper is concerned about comparing the different snapshots. And in this confusion matrix, the index corresponds to each snapshot, and they do the correlation of the hyperparameters on each snapshot. And on the image on the left, they restart the models randomly. So it's the standard ensembles, and the image on the right, it's their snapshot ensembles proposal. And we see that the image on the right, that the 4th, 5th, and 6th snapshots, they have the hyperparameters super correlated to each other. So again, those models are better, but they lose the diversity part, whereas in the normal ensembles, we get the full diversity.
So Lizzie raised the hand.
Yeah.
Can we give her?
Yeah, of course.
We let her speak.
Allowed to talk. Okay. Hello, Lizzie. I think. Wait, have we?
She has to accept. Oh yeah. Hello.
Yeah.
Hi. Yeah, I thought the colors in that confusion matrix were incredibly misleading. They've just rescaled the color scale to the min
Oh
and
yeah,
max of that matrix. So
I
you see
haven't
that
noticed that.
on the left-hand side, the 0.93 is really pale blue, even though
Mm-hmm.
that's a pretty large correlation. And in
Mm-hmm.
fact, on the left-hand side, the 0.88 is sort of the same shade as on the right-hand side, the 0.76. So yeah, they're actually really similar in the ensemble, the snapshot ensemble.
Mm-hmm. Yeah.
That was all.
Yeah. I agree. I think and I would expect the snapshots, the normal ensembles, to have a high degree of correlation. I think makes sense. But yeah, there is a very misleading color scheme.
Yeah.
Anyways, well, my point is, I find this paper, like the concept of exploring the lost landscape, is super interesting. But I would take the conclusions with a grain of salt, because I don't think they have made fair comparisons in general. Arvid asked another question. Do the pictures indicate that the last minimum is sharper than all others, at least for some data sets? I don't understand what you mean by sharper, so I'm going to give you the talk privileges. It's probably easier.
Hello, can you hear me?
Yes.
Perfect. If you scroll up to the pictures of the lambda plots.
These ones?
Yes, correct. Then say in the very leftmost paper plot, it looks as if you go from one minimum to the other, there's a relatively gradual slope in which the error grows, right? Whereas in the right ones, it seems that for the last snapshot, the error grows very, very quickly the moment you move away from it.
Mm-hmm.
But that also seems to be true then for the third and fourth and fifth snapshot, even though you would probably expect them to be getting as steep as the last one.
Mm-hmm.
I'm not sure how to interpret that.
I think what they are trying to do with these pairs of images is that with the cosine annealing, they are able to get away from the local minima and explore the space, whereas with the normal scheduling, you are not able to do that. And that's why the fourth and the fifth snapshot are pretty much the same as the sixth snapshot, because you are stuck in that local minima. You are not able to get away. At least that's my interpretation.
But the lambda equals 1 is the very last snapshot, right?
Yep.
So
yeah,
why does the very last one look so very different from all the others?
So by last one, you mean the purple one?
Oh yeah, or the lambda equals 1. So why is the plot asymmetric? At least if you expect higher numbers of snapshots, it should be symmetric again, right?
So this means that if you consider 90% of the sixth snapshot and 10% of the first snapshot, you have already ruined your results, which is strange, actually. It probably means that they have very different orders of magnitude.
Yeah, that could be.
But that's a hunch. I don't know how to actually fully answer that. We have another. Sorry?
Thank you anyways.
No worries. We have another question from the suspicious Alan Mosca, which is, what's your take on the relationship between restart and the studies that show that lost minima are connected by tunnels? Ooh, that's a good question. So I think where Alan is trying to get is that there are a few papers from ICML and ERIPS from last year that show that there are actually tunnels between minimum spaces. So you can go along that tunnel and keep having low loss. And this relates to this paper because every time they create a new snapshot, they start where the last one ended. So it could be the case that they are traversing the tunnel. However, I don't think that's happening here, because they show in their training loss, that the loss spikes up a lot. I mean, they couldn't be traveling through, well, some sort of tunnel where they have decent performance, but not the best performance. It could be the case. And yeah, it actually makes sense. Because after the first model, they will never go back up again to this regime.
Yeah, but if it's a tunnel in 3D, if you imagine it in 3D and you start here, you drop very quickly, then you up the learning rate, so you go out of the tunnel and then back down and then up and then back down and then up and then back down.
Yes, right? but I am thinking more on the case. So if imagine that you have again the 3D shape of a tunnel, and but you start from the bottom position and you increase the learning rate a lot. So you might be able to get into worst positions of the tunnel, but it could be the case that you are not able to fully escape the tunnel, because remember that the learning rate decays very fast because of the cosine function. So they are in some sense stuck in a tunnel of decency where they can't get very bad results again, which again cuts the diversity. That makes sense.
Yeah, I agree. That's that could be a problem with doing snapshots if you're just stuck in the same. So if the landscape does not look as nice as the one they showed first, but it's a bit more, it has worse conditions for this method.
So if there are no more questions, I think I am done with the presentation. And again, I think this is a great idea conceptually. And it's the idea of exploring the loss landscape has been having a lot of papers recently, because they are getting very good results when they do clever ways of exploring the loss landscape. However, we should take the results of this paper with a grain of salt. It's better than not doing nothing or not doing anything. But I think we could get into a better point using the same resources if we explore the normal ensembles correctly. And that's my opinion. So also take it with a grain of salt. Thank you very much.
Thank you, Joao.
Thank you. We can clap by a show of hands.
Thank you.
Okay.
Appreciate it.
Cool. Thanks, everyone. Yeah, thanks, everyone. So, I guess it takes a bit less to do this virtually, but as usual, we're going to keep doing it in this format, as it seems to be working well. We'll do again the same thing next week, so just be sure to join a couple minutes before we start. So if you want to hear the introduction on how to interact with Zoom webinar. And yeah, if you want to know more about NPlan, what we do, and why we are here, just go to nplan.io and feel free to navigate on the webpage, look at our GitHub repo, and feel free to write to us if you have any questions about Paper Club. And if you want to present something, it's also possible in this format. Okay. Thanks, Joao. Thank you, everyone, and see you next week.
See you next week.